So only wait, so just type yeah.
You understand?
No, it's not in quotes or anything. You just said that to me.
Okay.
Save all that.
So as is our way, and will be our way next year, if you want to retake the test, you need to have all your assignments in before you retake the test. So yeah, just keep that in mind. The test did have some issues, we fixed them. So we have a new unit on solutions and concentration. The unit that we use for the math part of solutions that determines concentration is called molar concentration. So this is a 1 molar solution. 1 molar solution. And then, believe it or not, I did not make this. I found it. Somebody else made that. And I'm like, yes. So we'll be talking about a concentration on Monday, mathematical concentration. Today we're going to talk about some solutions and mixtures and some classifications of things. And then here's the joke. A white bear and a brown bear go for a swim. The white bear dissolves. Why? There's a lot of overlap between this unit and the previous unit on intermolecular forces. Just FYI. So I'll let you see if you can figure out that answer later. All right, so when we're talking about solutions, we're talking about something dissolved in something else. And that something that gets dissolved is called the solute, and it gets dissolved into the solvent. So the solute gets dissolved into the solvent, and it forms the solution. So when you're making your Kool-Aid, I don't know if people still make Kool-Aid. Yeah, when you're making your chocolate milk, the milk is the solvent, and your chocolate syrup is the solute, and you mix them together, and off you go with the solution. Okay. So again, the solute is the stuff that goes in, the solvent is the stuff that dissolves the solute, and together they make up the solution. Now, the crazy thing about solvents and solutes is they can be any phase. For instance, most jewelry is a solution of metals. Your jewelry is not pure gold. 1, because it'd be really expensive, and 2, it wouldn't shine very well, and 3, it wouldn't be very durable. So what they do is they use a material that is very tough, like chromium or silver or cobalt, and then they add it to the gold to give it strength. This is an 18-karat gold ring, meaning it's 18 parts gold, 6 parts something else. The carat system is based on fractions of 24. So if you have 10-karat gold, it's 10 parts gold, 14 parts something else. So solutions can be any phase. We're going to look at electrolytes tomorrow. Electrolytes are solutions that conduct electricity because they contain salts. Okay. Salts are just anything that has a positive and negative ion. Remember, the positive ion is called a cation, and the negative ion is called the anion. So a salt is anything that contains a cation and an anion. So when you're like, I need my electrolytes, I got to drink my Gatorade, all you're really drinking is flavored salt water, and that's it, sugar and salt water. So hey, you just next time you're running around, and just like do your exercise on the beach, scoop up some seawater, boom, you're good. You got your electrolytes back. But that's all Gatorade is. It's just sugar water to give it flavor, and the electrolytes are just salt water, which you don't need all those electrolytes, by the way. So when things dissolve, here, let me come back to this. Oop, back. So when things dissolve, like salt here, remember, we learned this in intermolecular forces. When you have a bunch of sodium chloride, they're in a lattice, and then the water molecules come and they grab on to the ions. The partial positive part of the water molecule is attracted to the negative chlorine ion, and the partial negative of the water molecule is attracted to the positive part, the positive sodium ion. That's how they do their thing. So ionic compounds are electrolytes. Covalent compounds that dissolve are not electrolytes. So covalent compounds are like sugar. Sugar is very polar. Polar things dissolve in water. Remember? Polar dissolves polar. Non-polar dissolves non-polar. And you can use a conductivity tester to determine if something it conducts electricity. This is a conductivity tester I made about 11 years ago. I came to Boulder City, left all my conductivity testers somewhere else. So if you just touch them on something metal, then the lights come on. Question?
I got the joke. It's polar bear. I was thinking it was crystals because salts are usually pretty dissolvable. And also sometimes white because they're sometimes clear.
Yes. So the brown bear is just a brown bear, and the white bear is a polar bear. So the polar bear dissolves.
That's a good one.
I like that joke.
So some of these actually have a buzzer inside too. But yeah, so if I touch this on metal, then they light up, meaning electricity is able to travel through the little prongs. And if I touch them to solutions that are electrolytes, that's a good example. My little electrochemical cell here I made for AP Chem. If I touch them in here, light comes on because the solution is electrolyte. If I put them into a beaker of mostly well-filtered water, make sure it's a nice clean beaker. I haven't had a beaker before because I'm not clean. You guys got issues with cleaning your glassware. So if I put them into a beaker of relatively not Boulder City water, see, the little yellow light almost comes on, but this would be a non-electrolyte. What do you think Boulder City water is? Boulder City water. Get all your vitamins and minerals. If all those vitamins and minerals are calcium. So there's a lot of calcium, a little bit of copper, some magnesium in Boulder City water. Yeah, it's like you need to floss after you drink water here. But it's because there's ions in solution. So those ions make the water an electrolyte. Yeah, we're going to play with these tomorrow. Okay, questions so far? Off we go. Now, electrolytes can be strong or they can be weak. A strong electrolyte occurs when all of the ions disassociate, or all the salt disassociates into ions. So generally we talk about strong and weak electrolytes as strong electrolytes have a lot of ions. Weak electrolytes don't have as many ions. And the word we like to use is disassociate, literally come apart. So weak electrolytes conduct electricity very poorly because they don't have a lot of ions present. Strong electrolytes conduct electricity pretty well because they have a lot of electrolytes present, or a lot of ions present. And you notice that we would classify Boulder City water as a reasonably strong electrolyte because there's a lot of ions in there. Hey. Here we are. Okay, so moving on, and we're going to test a bunch of substances tomorrow. The word we use when things dissolve into other things is soluble, and when things don't dissolve into other things, we say they are insoluble. And we remember like dissolves like, polar things dissolve polar things, and non-polar dissolves non-polar things. Can't see it all that well, but if you put a bunch of solid in solution, the water will start attacking it and dissolving them. They are soluble. Soluble means able to be dissolved. Ionic solids, most of them are soluble. They dissociate into their ions. And covalent solids will be soluble when they are polar. And again, we learned this way back when we did intermolecular forces. Like dissolves like, polar dissolves non-polar, non-polar dissolves non-polar, polar dissolves polar, and polar also dissolves ions. So if it's a polar substance like water, it will dissolve other polar substances and ions, and non-polar, like wax or paraffin, will only dissolve into other non-polar things. And then once again, an alloy is a name that is a solution of metals, like your ring is an alloy, or your earrings or your bracelets or whatever if they're gold. Right? If you're with me so far, give me a thumbs up. It's a lot of me talking at you. Most of this is going to be me talking at you, but you're all going to have your own section here in a second. Now, the solubility is the amount of something that will dissolve. In other words, how good it is at dissolving things. And when we talk about solids dissolving in liquids, like salt dissolving in water or sugar dissolving in water, in general, for most substances, as you increase the temperature, the solubility rises. Okay. In general, there's cerium sulfate, which is weird, but in general, as you increase temperature, the solubility of most solids in water rises. So this is how they make candy. They take a bunch of water and they pour sugar in. And then eventually you can't pour any more sugar in. So they heat the water up. Now you can pour more sugar in. And they keep increasing the temperature and you can keep adding more and more sugar. So you get like a sludge. Okay. Gases work exactly the opposite way. Gases, their solubility is backwards. As you get warmer, the solubility decreases. If you watch the video, a few of you, they talk about fish. Fish want to live in very cold water because very cold water has a lot of oxygen dissolved in it. And you might know that fish breathe oxygen that's dissolved in the water. Colder water, more dissolved oxygen. And if you drink a lot of soda, love to be your dentist, if you drink a lot of soda, then you know that if you want your soda to stay fizzy, you keep it cold. You keep your soda in the fridge, that way when you pop the top, it doesn't lose all of its fizz right away. Because warm water will lose gases faster than cold water. Make sense? Okay. And we can also, how we get gases into water is with pressure. There is a little bit of carbon dioxide in pretty much all water that's just floating around. Like if I put some water in this beaker here, there's actually some carbon dioxide in here right now. And it's actually pulling carbon dioxide from the air faster and faster. But if I put it under pressure, I can force the carbon dioxide into solution and make what's called a carbonic acid or carbonated water. That's what they do at In-N-Out Burger. And Henry's law basically just says that the solubility of gases in liquids varies proportionally with the pressure. In other words, if you double the pressure, you can get more gas into liquids, which is what they do at the Taco Bell down the street. There used to be a formula that you had to use with Henry's law, but they got rid of the formula. So all you really need to know is more pressure, more gas in solution. Okay, we have 3 words we use to describe solutions and how much stuff they're holding. And those words are saturated, supersaturated, and unsaturated. These have nothing to do with fats. Fats use the same word for like saturated fat, trans fat, unsaturated fat. They use those similarly for the same purpose. But for us, we're talking about salts in solution or gases in solution. A saturated solution is one that has as much solute as it can hold at a certain temperature. As much solute as it can hold at a certain temperature, that's saturated. If the solution can hold more, then we say it is unsaturated. If there's room for the solution to absorb some more of the salt, we say that solution is unsaturated. And then if there is too much in solution and things start falling out of solution, if crystals start precipitating, we say it is supersaturated. So practically speaking, pressure in this room, weird. Okay, so practically speaking, oh, there it goes again. If you have a solution and there's salt sitting at the bottom, crystals sitting at the bottom, the solution is saturated. If crystals are forming at the bottom, it's supersaturated. And if you put some crystals in, they dissolve, it's unsaturated. Am I being clear? So unsaturated, you can put more. Saturated, you're done. Super saturated, they're going to start coming out. Okay. So when you go to Taco Bell to get your drink, they make soda pretty interesting. What they do is Coca-Cola will ship Taco Bell a bag of syrup. No joke. It's a bag of syrup. And then what Taco Bell does is they connect their giant tank of carbon dioxide to tap water. The same water that would otherwise go to the toilet. And all they do is they push carbon dioxide into the tap water, and that makes carbonated water, which gives it the fizzy, and they add a little line of syrup as you're getting the drink, and that makes your Coca-Cola. Yeah. So some you can actually see when you watch, it'll have like this little line of brown in the middle. That's the syrup that gives it the flavor. And the other stuff is just carbon dioxide from a tank in the back of the store, and then tap water. That's how they make soda. Did I show you guys this? How to open a soda with a Sharpie?
No, you didn't.
I'll show you tomorrow. We're gonna one of the electrolytes we're gonna test tomorrow is Coca-Cola or Pepsi or Sprite or so whatever is in the fridge, and I'll show you how to open a soda with a Sharpie. It's pretty cool. Okay, so imagine you got a can of soda, not open yet. You got a can of soda, it's under pressure. With respect to the gas in the soda that makes the fizzy bubbles, before you pop the top, is it saturated with gas, carbon dioxide? Is it unsaturated with carbon dioxide? Or is it super saturated with carbon dioxide? So think about that one for a second. Before you pop the top, is it saturated, super saturated, or unsaturated? With the gas in the thing, gas in the soda, I haven't popped the top yet. All right. Who thinks that the soda is unsaturated? You can put some more carbon dioxide in there. Nobody. One. Okay. Who thinks it is saturated? It's holding as much carbon dioxide as it can hold. 1, 2, 3. Okay. Who thinks it's super saturated? The carbon dioxide is coming out. A few of you. The three of you chose saturated are right, because the carbon dioxide it's holding as much as it can hold at that pressure. Okay. The carbon dioxide is holding as much, or the soda is holding as much carbon dioxide as it can at that pressure. But then you pop the top. Gas escapes. Now, after you pop the top, is it saturated, unsaturated, or super saturated? Think about it for a second.
It's saturated.
It's super.
Why do you say super?
Because the compression is different.
Yeah.
It's like really...
But what's the hallmark for a supersaturated solution?
There's crystals.
There's crystals, it's a solid. If it's a gas, it's bubbling up. So if the solute is leaving the solution on its own, it is super saturated. So before you pop the top, it's saturated. All the gas is still in there. And you pop the top and the gas escapes, and it keeps escaping. So if you take a pop, if you put a pop can on the table and pop it and then walk away, you come back an hour later, it's mostly flat.
Yes.
Because gas has escaped. So it's super saturated because the gas is escaping. And then if you leave it there for a couple hours and you come back and it's flat, what is it when it's flat? Saturated.
Okay.
Yeah, it's as saturated as with carbon dioxide as it goes. So before you open it, it's saturated. After you open it, the bubbles are coming out telling you it's super saturated. And after you shake it or leave it for a while and it goes flat, it's just saturated. Again, it's just pretty fun. Okay. Any questions about this before we move on? All right. We classify mixtures as three different things: as solutions, which we just talked about, or suspensions or colloids. Solutions dissolve into each other. A solute dissolves into a solvent to form a solution. Sometimes you get particles that are so big they settle out. That's what you get in a suspension. In a suspension, the particles are so large they cannot settle out. You have obvious phases. This is a suspension of muddy river water. Not really, dirt in the water. But if you shake it up, you see how it had settled before? So there's a lot of particles, and you can actually see them. There's like big particles. And I'll leave it here. It'll settle out again. That's a suspension. So a suspension has particles that are so large, you can actually see phases. The typical example for a suspension is Italian salad dressing. Italian salad dressing has obvious phases. You have to shake it up because there's an oil phase and a water phase. There's particles in there. That's a suspension. Very big particles, too big to dissolve. And in between, a solution where the particles are small enough to dissolve, and a suspension where the particles are so large they settle out, is this crazy type of mixture called a colloid. Colloids are cool. Colloid particles are so large they can't dissolve, but they're not large enough to dissolve. They're right in the middle. So what they do is they form this mixture that gets dispersed. In fact, the words we use for solutes and solvents are the thing that that would be the solute is called the dispersed phase, and the thing that would be the solvent is called the dispersing medium. You might be familiar with colloids. Foam is a colloid. Foam is a colloid where gas is trapped in liquid, or gas is trapped in solid. Smoke is a colloid of solids trapped in air. That's a colloid. Mayonnaise is probably one of your favorite colloids. Mayonnaise is liquid oil or liquid egg whites trapped in liquid oil. That's what mayonnaise is. It's egg whites in oil. Yum. It's like, mayonnaise, I love it. Yum.
Doesn't look like he knows him.
He looks like he's having a good time.
I don't think so.
He's like, mayonnaise.
This looks like something that, you know, like when colleges like relish, that's like something.
Take your word for
That's
it.
what I think of.
Okay, so that's a colloid. Now here's the thing about colloids. If you've ever done the I'm Luke Skywalker with my lightsaber in smoke, you like take your lights, you maybe you go camping and you got your flashlight and you shine your flashlight into the smoke around the fire. You're like, ooh, I'm back on my lightsaber. What you are doing is what's called the Tyndall effect. John Tyndall came up with this idea. He said, you know what? Sometimes it's hard to differentiate between a solution and a colloid. What I have up here is a solution and a colloid. Which one's the colloid? Which one's the solution? Kind of hard to tell, right? Watch this. Got a laser, right? Can you see the beam?
Yeah.
Can you see the beam?
No.
When you can see the beam through something, it tells you it is a colloid. This is called the Tyndall effect because the beam goes right through the solution, but then you can see it in the colloid. That's the Tyndall effect. So if you can see light bounce off the particles, then it's a colloid. If the particles are so small they dissolve and light does not bounce off of them, then it is a solution. And obviously suspension blocks the light right away. Right? That is the Tyndall effect. Just like here. This would be a solution, this would be a colloid. So if light gets blocked, it's a suspension. If it passes right through unobstructed, it's a solution. And if it travels through, but you can see it refracting off little particles in there, then it is a colloid. Just like here. All right. If you're clear so far, give me a thumbs up. If you have questions, wave your hand around. We're almost to the part where you actually get to do something. Okay, so salts are composed of positive and negative ions. The positives are called cations, and the negatives are called anions. And when those salts dissolve into their ions, we get what's called a disassociation equation. That is a disassociation equation for sodium chloride. So the sodium chloride dissolves into its ions sodium and chlorine. I have a question for you. How many moles of ions are present in a solution of 1 mole of sodium chloride? If I had a mole of sodium chlorides, 58 grams, how many moles of ions do I have present? Evan, what do you got? 2. Yeah. You got a mole of cations and a mole of anions. So if you have a mole of salts, you'll have a mole of cations and a mole of anions. See how that works? Disassociation into its ions. Okay, if that is clear to you, give me a thumbs up. Okay, because what I'd like you to do now is I would like you to finish the disassociation equations for these 3 and determine, so first finish the disassociation equations, and then, positive, negative, determine how many moles of ions are present if you have 1 mole of the salt. So do that now. Isn't it? Remember about polyatomics? Polyatomics act as 1 unit. Shouldn't have your phone out unless you were actually using it as a tool. Curse this front seat. Let's take a look. See how we did. What's the cation in copper sulfate? Copper. So we got 1 copper and 1 sulfate. Remember, sulfate's -2, copper is +2. So how many total moles of ions do you get per mole of salt? Here. 2. 1, 2. Magnesium, they make it easy on this one. Magnesium nitrate. So magnesium and nitrate. You get 2 nitrates. So how many total moles of ions? 3. And for sodium carbonate, also 3. Make sense? Okay.
So the
Yeah.
So the subscript, like it's because it's Na2 on the left, so those change to Na.
Correct. Because Na is not diatomic, it's just Na. So this tells you, remember, if you remember our compounds, you have carbonate is -2. That means you need 2 sodiums to balance out the carbonate. So these 2 sodiums become 2 Nas and then carbonate. And same here, magnesium is +2 because it's in group 2, nitrate's -1. So it's magnesium 2+ and 2 nitrates. If this is clear, give me a thumbs up. If you have further questions, wave your hand around. Okay, can I help you?
I'm confused because on the first one it was 2, right?
Yes.
The CuSO4.
2, yes.
And then, so why did it change to 3 on the other ones?
1, 2, 3. 1, 2, 3.
So just the amount of what there is? Okay.
Yep. So every time the salt dissolves, it releases its ions. With sodium chloride, it releases 1 cation, 1 anion. Copper sulfate, 1 cation, 1 anion. Magnesium nitrate, 1 cation, 2 anions. Sodium carbonate, 2 cations, 1 anion. Any other questions? Cool, that's all I have for today. So if you haven't got a chance to do the videos, because they're really good. And then we'll actually do some math on Monday.